Just a heads up that some of the slides have animations, but since we've switched from a Mac to, I guess it's a Windows, I would hope that the animation doesn't get screwed up. But let's see what happens. So my name is Seshank Kalvala. On stage with me is Sahil Ramrakhyani. We are developers from Salesforce.com. We are here to represent our team's ongoing work on querying big object data on Salesforce platform using Phoenix statistics. So this slide is essentially a disclaimer. What it says is that if you are a Salesforce customer looking to buy Salesforce products, you should base your decisions on products and features that are already out there in the market and not base them on projects that are in development like the ones that we are about to present. This is the agenda of our presentation. We'll start off with giving you an overview of Salesforce platform and how the notion of big object data is supported on Salesforce platform. We'll then introduce you to a language called SOQL. It stands for Salesforce Object Query Language, how we use that to query the big object data, what are some of its current limitations, and how we are looking to enhance the query support on big object data using SOQL, using Phoenix Stats. We'll then deep dive into what Phoenix Statistics is, how it works, and how we are consuming it at platform layer to try to enhance the query support. And finally, we'll conclude our presentation with some forward-looking action items pertaining to Phoenix. So Salesforce platform, it's essentially a leading platform that's provided as a service for hosting business applications for customers. So in simple terms, what that translates to is customers can use the in-house Salesforce products and features that cater to their business needs, or they can develop their own custom applications, but have all of them run in the Salesforce data center so that they need not worry about setting up the software or the hardware infrastructure. And the notion of big data is supported on Salesforce platform via a feature called Big Objects. In today's world, all companies want to capture data about their consumers. They want to be able to store this data. They want to be able to manage this data, operate on it, analyze on it. And Salesforce Big Objects is a way to do that on big objects within the Salesforce platform. This is the technology stack that's involved in supporting the big object architecture within in Salesforce. The box in purple that you see, which says Big Object Framework, that's the layer that our team deals with. It falls within the umbrella of Salesforce platform. Below that, as you can see, we leverage on open source technologies. We use Apache HBase to store the big object data. We use Phoenix to interact with this data and query the data. And we use Hadoop MapReduce to perform computations on this big object data. Now I would like to introduce you to a language called SOQL. It stands for Salesforce Object Query Language. It is a language that is native to Salesforce platform and is used to query Salesforce data specifically. It was designed for that purpose. It is syntactically very similar to SQL, which stands for Structured Query Language. So if you are familiar with SQL, it's very easy to run and execute SOQL statements. The cool thing about SOQL on big object data is that the query performance is constant and independent of data size. The way we achieve this is in the big object framework. We have checks and balances to ensure that when a query is executed, it does not result in unbounded scans or full table scans. However, because of that, we also have some limitations on the SOQL query flavors that can be executed on big objects today. As an example, if you have a select statement, you can only perform filter operations on indexed fields. However, you cannot perform select statements on non-indexed fields. Similarly, we do not support aggregate functions, group bys, having clause, to just name a couple. As an example, so consider a big object by name of big order item, and it has order ID and item number as the indexed fields. And so this particular SOQL query will go through because the filter conditions have the indexed fields in them. Whereas if you issue a select query on any other column, then that query will not be permitted for execution. And these are some of the current limitations, and we want to be able to break away from these limitations and provide more flexibility in the sort of query patterns that can be issued on big object data. One thing to bear in mind is if we want to provide more query support, we need to make sure that the query response time falls within an acceptable predefined time limit. We don't want someone to issue a query and sit there for minutes or hours and wait for the query to get back with the results, especially when we are operating in the big object world. So how exactly can we determine whether a query can be permitted for execution or not? And that's where we essentially perform an analysis of the query at runtime using Phoenix statistics and determine whether we want to run the query or not. At this point, I'll hand over the mic to Sahil, who will run you through what Phoenix Statistics is and how it is consumed at Salesforce platform layer to enhance our query support. Sahil.
Thank you, Shashank. As Shashank mentioned that the Phoenix statistics is a way to determine the query complexity at runtime. Now, before we deep dive into how Phoenix statistics does that, let's start with what is Phoenix statistics and how it works. So, Phoenix statistics, what is it? It's a way of partitioning the HBase key range scan into set of equal buckets, and then it stores the information of those buckets into system.stats table. So it basically takes the key range scan, divide into set of equidistant marker, stores those marker into the tables. Those marker are also known as guidepost. In addition to that, it also stores information about the size of each bucket and the number of rows in each bucket. Now the question comes, how does Phoenix determines the size of each bucket? That's been determined using the parameter configuration setting known as guidepost width. This configuration setting is set at each table level, that is each HBase table can have a separate guidepost width. And optimal guidepost width depends on a lot of factors like cluster size, cluster usage, disk IO, table size. Based on multiple factors, one can determine the optimal guidepost width for a given table. Next is Phoenix Statistics usage. As some of you here might know that Phoenix Statistics has been widely used for query parallelization, that is using the guidepost information. It's used to determine whether that query can run across multiple region server. Now we went a step ahead of that, and rather than using Phoenix Stats for query parallelization, we enhanced the Phoenix Stats to use the statistics information to determine the query complexity at runtime. And how do we do that is we use the guidepost information which we store in system.stats to determine estimated number of bytes that query will take based on its query filter parameters and based on the guidepost information. Now, how do we surface this information to the client, to the application layer? So that's been surfaced using the explain plan. The syntax is straightforward, it's explain, and then you give the query for which we need to determine the complexity, and based on that explain plan returns okay which HBase table it will scan, what operation would be performed at server side or client side. In addition to that, in addition to this query plan, now it also gives the information about estimated number of bytes read for that query and also the estimated number of rows read for the given query. And this is all using the Phoenix stats information. One thing to note here is the estimated number of bytes read is always the multiple of guidepost width. That is, accuracy can never be granular than guidepost width. So that's another factor when we decide the optimal guidepost width for a given table. Phoenix architecture, a lot of you would be familiar with this architecture. In this talk, we'll cover how Phoenix statistics is incorporated at each level, that is at the server level, then how it's interacted at the client level, and finally to the application level. So let's start with Phoenix stats collection, how it works at the region server or the Phoenix coprocessor level. So how does Phoenix stats collection works? Phoenix stats collection is independent for each region. That is, each region collects the stats independently. Now it's a two-step process. In step one, it goes through all the keys for a given HBase table in a given region. So let's say for our example, we have this given table and these are our indexed field and these are non-indexed field. So as a step one, it goes through all the key range scan for a given HBase table and collects the keys which are equal distant from each other based on the guidepost width parameter. And once it is done with collecting all the keys for a given region, it stores those keys into in-memory representation. Once all the keys has been collected, as a step 2, it stores that information into system.stats table. So first it deletes the existing data from system.stats for that table, and then it inserts the new data from the in-memory representation. And this is all done as a single RPC call. And it updates the information in system.stats, and we can see it contains the table name and the guidepost key, and also when was this information last updated. Now, what are various ways by which we can trigger stats collection on the server side? So there are two ways by which the Phoenix stats collection can be triggered. One is manual way, where you give explicitly the command update stats for a given table, where it will go and update the stats for that particular HBase table. Or another way is during the major compaction. So during major compaction, Phoenix coprocessor goes and updates the stats for all the regions. So this, we saw how stats collection work on the server side. Now next part comes is how Phoenix client use this information and determine the estimated number of bytes. So one of the component of Phoenix client is Phoenix client cache. Phoenix client cache stores the information of system.stats table. That is, it contains the content of system.stats table in the client cache. Now how it works is, as a step 1, when application asks for an explain plan from the Phoenix, at that time Phoenix client determines, based on the query parameters and based on the guidepost information, whether the information is up to date to cache and whether it has all the information in the cache. If yes, then it determines the estimated number of bytes required for that query to scan, and it returns it to the application. But in case of cache miss, that is, the data is expired in cache, or if the data is not available in cache, in that case it goes to the server, request for the updated information, and thereby once it gets the updated information from the server, at that point it goes and returns to the application the number of bytes for that query. Some points to note here is Phoenix client cache has a property called TTL, which specify that after how much time the cache content would be expired. And also another property is this cache is lazily loaded. Only when the application asks for the explain plan, at that point it checks whether the cache contents are expired or not. Next part is, so we talked about how it works on the server side, how Phoenix client interacts with the server to get the stats information, and how it returns the estimated number of bytes to the application layer. Now Seshank will talk through how application layer uses this information to determine the query complexity and at the runtime. Seshank.
Thank you, Sahil. So we've seen how the Phoenix stats information is surfaced to the Phoenix client via the explained plan. Now we'll look at how Salesforce platform as an application consumes this information and determines whether to run a specific query that's been issued on big object data. So in one of the prior slides, I had said that we want to make sure that the query response time falls within an acceptable predetermined time limit. What that would translate to is, if you want to have a query response time within a predefined time limit, that means we would want to have a predefined number of bytes that can be scanned for a given query. And if a query is issued, we don't want the number of bytes to scan to exceed this predetermined limit. So in this example, the ones that you see in caps called max bytes allowed, that is the predetermined maximum number of bytes scannable when a particular query is issued. And so now we get the stats information from the Phoenix client, and we are able to get the estimated number of bytes that would be scanned for a specific query. We compare the estimated number of bytes that would be scanned with the max bytes allowed. If it is less than max bytes allowed, we essentially process that query and return the results back to the user. If the estimated bytes to scan ends up being greater than the max bytes allowed, we essentially fast fail the query and throw the appropriate error message back to the user. So this particular slide essentially shows how the query flow would be from the context of the application layer. So here we have an end user. The end user issues an query on the big object. The big object framework will try to get the estimated number of bytes to scan for the query issued by asking the Phoenix client. The Phoenix client returns the estimated number of bytes to scan. And then the framework, we compare the estimated number of bytes to scan with the predetermined threshold that we have set, and which in this case is the max bytes allowed that I showed in the previous slide. If the estimated bytes to scan ends up being less than that threshold, we essentially process that query and then we return the results back to the user. If it ends up being more than the threshold, we essentially fast fail the query and throw the error back to the user. And this is just one other example query to drive home the point. This slide assumes that, let's say, the max bytes allowed, or in other words, the maximum number of maximum number of bytes that is scannable, let's say we are setting it to 500 MB. This slide also assumes that the guide post width is 100 MB. And so if you are executing the query that you see on the slide, and the Phoenix stats, we determine that that involves scanning 3 guide posts worth of data. That translates to scanning 300 MB, bytes of data. And since that 300 MB is less than 500 MB, we'll go ahead to execute this query and then return the results to the user. If it were the case that Phoenix Stats had told us that you'll have to scan more than 5 guide posts worth of data, that would translate to scanning more than 500 MB of data, and so the query would be fast failed and the appropriate error message would be returned back to the user. And to conclude, here are some of the forward-looking action items that we are looking to get a closure on pertaining to Phoenix. One is we would want to have the cache as non-blocking. Currently, it is blocking. What we mean by that is if a query is issued and that results in a cache miss, then essentially the Phoenix client will try to get the updated stats from the coprocessor. But while this is happening, if any other query is issued at the same time and that also results in a cache miss, then that particular query will be put on hold until the first query has been processed through. But if we make the cache non-blocking, then we can have multiple queries executed in parallel. And if several of them hit the cache miss, we can process them in parallel rather than have them execute sequentially. So that's what it means by making cache non-blocking. We also want to have the cache implementation as pluggable. So if there's a better cache implementation in the future, we want to be able to swap our existing implementation with whatever better implementation we come across. Another aspect to consider is how frequently do we want to run the stats collection process, because if we don't run it frequently enough, then the stats will be out of sync with the actual data that's lying on the HBase. So we want that information on HBase to be in as much sync as possible with the Phoenix stats. There's also this aspect of what happens when the stats collection is in progress and then there's a failure. How exactly would one detect it and how would one want to recover from it? That's one aspect that needs to be investigated into. And finally, there are a couple of limitations as far as getting the estimated bytes to scan from explained plan goes. We detected 1 or 2 query flavors for which Jira bugs have been filed, where the estimated bytes to scan, they are not accurate. We found that out during our testing. And so those need to be looked into and fixed as well. That pretty much concludes our presentation. And here are some references on how stats collection works at the Phoenix layer. We also have links on big objects and how they are supported on the Salesforce platform. So yeah, so if you have any questions, I don't know if you have time. Okay. Sure. Yeah, so apparently we are running short on time, so we can take it offline if anyone has any questions. Thank you so much. Appreciate it.